Across the immense, flattened plain of the Milky Way, a spiral structure of 100 billion stars turns in a slow, majestic wheel of light and gravity, a rotation so vast that a single circuit requires more than 200 million years to complete. This is our galactic home, a city of suns bound together by a central, supermassive black hole and the invisible scaffolding of dark matter. Its arms, traced by the brilliant blue light of young, hot stars and the pinkish glow of ionized hydrogen nebulae, are regions of constant birth and renewal. Here, in the relative thinness of the galactic disk, our own sun moves through its long, quiet life, part of a sprawling, luminous suburbia. But beyond this vibrant, active plane, in the vast, spherical volume of space that surrounds it known as the galactic halo, reside the galaxy's most ancient citizens. These are the globular clusters, self-gravitating, spherical collections of hundreds of thousands of stars, each one a relic from the dawn of the universe, a fossil of the Milky Way's own formation. They drift on long, elliptical orbits that plunge through the galactic disk and soar high above it, silent witnesses to the entirety of cosmic history since the first galaxies began to coalesce from the primordial gas. Among these venerable assemblies, one in particular holds a position of unique significance, not for its size or its brilliance, but for its proximity. It is called Messier 4, a name given from a catalogue of celestial objects compiled in the 18th century, a simple designation for what was then just a faint, fuzzy patch of light in the constellation Scorpius. Today, we know it as one of the very closest globular clusters to Earth, lying at a distance of approximately 7,200 light-years. This relative closeness transforms it from a mere point of light into a resolved laboratory of stellar evolution and dynamics. Through our most powerful telescopes, Messier 4 is not a blur, but a breathtaking swarm of individual, ancient suns, a sphere of golden and reddish light packed so densely toward its center that the stars appear to merge into a single, continuous glow. It hangs in the sky near the brilliant, fiery orange supergiant star Antares, the heart of the Scorpion, a celestial juxtaposition of the ephemeral and the eternal. Antares, for all its dazzling power, is a star destined to live for only a few million years before exploding as a supernova. Messier 4, its quiet neighbor, has already persisted for more than 12 billion years, its stars having shone since the universe was less than a tenth of its current age. Within this ancient, nearby sphere of stars, a profound and subtle mystery is unfolding, a mystery written in the precise, silent motions of its central members. Their dance suggests the presence of something unseen, a concentration of mass that does not shine, a gravitational anchor hidden within the cluster's luminous heart, questioning our understanding of how these primordial stellar cities live, age, and perhaps, what they ultimately become. The light that reaches us from Messier 4 tonight began its journey when civilization was first emerging in Mesopotamia, and encoded within that ancient light is a secret about the nature of gravity, the life cycle of stars, and the unseen architecture of the cosmos itself, a secret that whispers of an object that should not, by some measures, be there at all. The cluster's serene appearance belies a dynamic and violent past, and a present condition of gravitational tension that points toward a central, dark enigma. The story of Messier 4 is not just the story of a collection of stars, it is a search for a missing link in the grand evolutionary chain of cosmic structure, a search for a ghost in the galactic machine. And it begins with the simple, yet powerful observation that in the very center of this stellar metropolis, the stars are moving far too fast, orbiting a center of gravity that is heavier and more compact than all the visible light can account for, a gravitational anomaly that has commanded the attention of astronomers for decades, a puzzle whose solution may lie in the existence of a type of object long theorized but maddeningly difficult to confirm, an intermediate mass black hole. The steady, ancient light of Messier 4 is therefore not just a beautiful sight, but a message from the deep past, a complex dataset traveling across interstellar space, carrying with it the subtle, gravitational signature of an invisible sovereign ruling from the center of this stellar kingdom. To journey from our own solar system to the heart of Messier 4 is to traverse a distance that defies human intuition, a chasm of space so vast that light itself, the fastest thing in the universe, requires more than 7 millennia to cross it. The journey begins by leaving behind the familiar planets, the asteroid belt, the Kuiper belt, and the distant, frozen Oort cloud that marks the outer gravitational boundary of our Sun. From here, the Sun shrinks to become just another star, indistinguishable among the countless billions that constitute our local spiral arm. The path leads inward, toward the dense and luminous core of the Milky Way, crossing vast, cold expanses of interstellar medium, a near-perfect vacuum punctuated by diffuse clouds of gas and dust, the raw material for future generations of stars. For thousands of years, the traveler would move through this darkness, guided by the growing concentration of starlight ahead. As the destination grows nearer, the constellation Scorpius would dominate the view, its familiar shape distorted by the new perspective. The star Antares would swell into a colossal, luminous sphere of orange light, a supergiant star so large that if it were placed at the center of our solar system, its surface would extend beyond the orbit of Mars. And just beside this stellar behemoth, a faint, nebulous patch would resolve itself into a staggering spectacle, the globular cluster Messier 4. From this closer vantage point, the cluster is revealed not as a gentle smudge, but as a gravitationally bound sphere of immense age and complexity. It spans approximately 75 light-years from one edge to the other, a self-contained island universe of stars. Its total mass is estimated to be around 100,000 times that of our Sun, a collective weight that holds its hundreds of thousands of constituent stars in a perpetual, intricate dance. The age of this system is almost incomprehensible. Models based on the chemistry and brightness of its faintest stars place its formation at around 122 billion years ago. This means the stars of Messier 4 were born when the universe itself was only about 15 billion years old. They are first or second generation stars, forged from hydrogen and helium gas that was only lightly seasoned with the heavier elements cooked in the cores of the very first, short-lived stellar giants. This ancient origin is reflected in their composition. They are metal-poor, containing only about a tenth of the heavy elements found in our own Sun, a chemical signature that marks them as true relics of the early cosmos. Unlike many other globular clusters, which are extraordinarily dense and compact, Messier 4 is considered a relatively loose or low-concentration cluster. Its stars are more spread out, particularly in its outer regions. This structural characteristic makes it easier for astronomers to resolve individual stars even near its crowded core, a crucial advantage in the hunt for its central secret. Visually, the cluster is a stunning gradient of stellar density. The periphery is a sparse sprinkling of stars against the black of interstellar space. Moving inward, the population thickens, the average distance between stars shrinking from light years to light months, and then light weeks. At the very center, the density becomes extreme. Here, in the core, the average distance between stars is a mere fraction of a light-year, thousands of times more crowded than the Sun's own stellar neighborhood. An observer placed on a planet within this core would see a night sky not of blackness punctuated by points of light, but a continuous, blazing canopy of suns, a sky where true darkness never falls. It is within this intensely crowded, gravitationally fraught central region, a space only a few light-years across, that the laws of stellar dynamics play out in their most dramatic form, and where the evidence for a hidden, massive object is most profound. The light we see is the collective glow of these ancient suns, each one a testament to endurance, a slow-burning fire that has lasted for nearly the entire age of the universe. Within the confines of Messier 4, the laws of physics operate on a timescale and at a density that transform a collection of stars into a single, evolving entity. This is a stellar city, and like any city, it has a structure, a dynamic, and a history of settlement and migration dictated by a fundamental principle, gravity. Over the course of 12 billion years, the cluster has had ample time to undergo a process known as dynamical relaxation. In this process, the constant, gentle gravitational tugs between individual stars as they pass near one another act like a form of friction, slowly redistributing kinetic energy throughout the system. Over eons, this leads to a state approaching thermal equilibrium, where lighter, faster-moving stars tend to gain energy from encounters and migrate towards the less dense outer regions, or the halo, of the cluster. Conversely, the most massive stars and stellar remnants lose energy in these gravitational exchanges, causing their orbits to decay and shrink, forcing them to sink inexorably toward the cluster's gravitational center. This process, known as mass segregation, is the cluster's natural sorting mechanism, an invisible, patient force that concentrates its heaviest components into its core. The result is a stratified stellar population, a celestial archaeology where the most massive and often darkest objects lie buried at the center. The population of Messier 4 is a testament to its advanced age. The vast majority of its stars are low-mass, cool, and long-lived, shining with a reddish or yellowish hue. The massive, brilliant blue stars that once populated the young cluster have long since exhausted their nuclear fuel, exploding as supernovae billions of years ago and leaving behind their compact corpses. What we see today is a mature population of main-sequence stars, similar to our Sun but much older, alongside a prominent number of red giants, stars that have entered the final phases of their lives, swelling up to enormous sizes and shining with a brilliant, cool luminosity. But the most interesting residents, particularly in the context of the central mystery, are the exotic objects born from stellar death. Deep within the cluster's core, concentrated by mass segregation, lies a graveyard of stellar remnants. This includes a vast, unseen population of white dwarfs, the hot, dense cores of sun-like stars, each one packing the mass of a sun into a volume the size of the Earth. Even more extreme are the neutron stars, the ultradense remnants of supernova explosions, where the mass of 1.5 suns is crushed into a sphere only 20 kilometers in diameter. A single teaspoon of neutron star material would outweigh a mountain. In Messier 4, a remarkable number of these neutron stars have been detected as millisecond pulsars. These are ancient neutron stars that have been spun up to incredible rotational speeds, hundreds of times per second, by accreting matter from a binary companion star. They sweep beams of radio waves through space like cosmic lighthouses, their precisely timed pulses providing astronomers with invaluable tools for probing the cluster's gravitational environment. And alongside these white dwarfs and neutron stars, theory predicts the existence of the heaviest remnants of all, stellar mass black holes, formed from the collapse of the most massive stars in the cluster's youth. Each of these objects, weighing between 5 and 20 times the mass of the Sun, would have sunk to the very center of the cluster over the ensuing eons, forming a dense, dark nucleus. It is this dynamic, crowded, and gravitationally stratified environment that sets the stage for the central puzzle. The visible light of the cluster tells only part of the story. The true nature of its core is dictated by this hidden population of compact, massive objects, a population whose collective gravity shapes the orbits of every star around them. The dance of the visible stars is merely a reflection of the unseen mass that governs them from the center of this ancient, stellar city. The first hints of a profound anomaly at the heart of Messier 4 emerged not from a sudden discovery, but from the patient accumulation of precise, painstaking observations over many years. The central question was a simple one: how fast are the stars in the cluster's core moving? The answer, however, required pushing the limits of astronomical instrumentation. Astronomers employ two primary techniques to measure the motion of stars. The first is spectroscopy, which analyzes the star's light, splitting it into a rainbow-like spectrum. Within this spectrum are dark lines corresponding to specific chemical elements in the star's atmosphere. If a star is moving towards us, these lines are shifted slightly towards the blue end of the spectrum. If it is moving away, they are shifted towards the red. This phenomenon, the Doppler effect, allows for the measurement of the star's radial velocity, its speed along our line of sight. The second technique measures proper motion, which is the star's movement across the plane of the sky. This is far more challenging for distant objects like those in Messier 4, as the apparent movement is minuscule. It requires taking high-resolution images of the same patch of sky years or even decades apart and meticulously measuring the tiny shifts in the positions of thousands of individual stars relative to one another. By combining the power of the Hubble Space Telescope for its sharp imaging capabilities and ground-based observatories like the Very Large Telescope for their sophisticated spectrographs, astronomers built up a detailed three-dimensional velocity map of the stars in Messier 4's core. They tracked the movements of hundreds of stars within the central few light-years, creating a dynamic picture of the cluster's heart. When they analyzed this data, a clear and disturbing discrepancy became apparent. The stars were moving too quickly. According to the laws of gravity, the speed at which a star orbits a central point is determined by the amount of mass contained within its orbit. By counting the stars, estimating their individual masses based on their brightness and color, and summing them all up, astronomers could calculate the total visible mass of the core. This calculation yielded a prediction for how fast the stars should be orbiting. But the observed velocities were significantly higher. The stars were whipping around the center as if they were being gripped by a much stronger gravitational field than the visible matter could possibly generate. This is the classic signature of hidden mass. Something unseen, something dark, was present in the core, adding its gravitational influence to the total, accelerating the stars beyond their expected speeds. The discrepancy was not subtle. It pointed to a concentrated mass of several hundred solar masses packed into a very small volume, a region no more than a light-year across. The visible stars and their known remnants simply could not account for this gravitational excess. The data strongly suggested a central, dark concentration of matter, a gravitational anchor holding the core stars in their swift, tight orbits. This whisper of hidden mass, inferred from the silent, precise dance of ancient suns, opened a profound new chapter in the study of Messier 4. It transformed the cluster from a simple, beautiful collection of stars into a laboratory for studying the most extreme and enigmatic objects in the universe. The puzzle was now clear: what was this unseen mass? Was it a single, monolithic object, or a collection of smaller, dark bodies? The evidence pointed toward something extraordinary, a type of object that represents a critical but missing piece in our understanding of cosmic evolution. The frantic, hurried orbits of the innermost stars were a gravitational cry, a signal broadcast across 7,000 light-years, testifying to the presence of a hidden sovereign at the center of their ancient kingdom. The search was on to identify this invisible ruler, and the leading suspect was an object of immense power and mystery, an intermediate-mass black hole. The suspect at the heart of Messier 4 belongs to a theoretical class of objects that has long haunted the field of astrophysics, the intermediate-mass black hole, or IMBH. These are the universe's missing middleweights, objects that bridge the vast chasm in mass between the two well-established families of black holes. On one end of the spectrum are the stellar mass black holes. These are the common endpoints of life for the most massive stars. When a star more than 20 times the mass of our Sun exhausts its nuclear fuel, its core collapses under its own immense gravity, triggering a supernova explosion that blasts its outer layers into space. The core, however, continues to collapse indefinitely, crushing matter out of existence and forming a black hole with a mass typically ranging from a few to a few dozen times that of the Sun. Thousands of these are thought to roam our own galaxy. On the other extreme are the supermassive black holes, the gravitational titans that reside at the centers of nearly all large galaxies, including our own Milky Way, which hosts Sagittarius A, an object of 4 million solar masses. The most massive of these cosmic monsters can weigh in at tens of billions of solar masses, their gravitational influence shaping the structure and evolution of their host galaxies on the largest scales. Between these two well-documented populations lies a vast and conspicuous mass gap, where are the black holes with masses of hundreds, thousands, or tens of thousands of solar masses. For decades, evidence for their existence was scant and often ambiguous, leading some to wonder if nature simply did not produce black holes in this intermediate range. Yet, their existence is a crucial prediction of our theories of cosmic structure formation. Supermassive black holes could not have sprung into existence fully formed, they must have grown over cosmic time. The most plausible mechanism for this growth is that they started as smaller seeds, and grew by accreting gas, dust, and stars, and by merging with other black holes. Intermediate-mass black holes are the most logical candidates for these seeds. Finding them would provide the missing link in the evolutionary chain that connects the death of a single star to the formation of the galactic behemoths that govern entire galaxies. They are the missing adolescents in the family album of black holes, the crucial transitional stage that would complete the story of their lives. The hidden mass in Messier 4, estimated from the frantic orbits of its central stars to be approximately 800 times the mass of our Sun, fits perfectly within this theoretical IMBH mass range. If confirmed, it would be one of the most compelling candidates for an IMBH ever discovered, and its location in such a nearby, well-studied globular cluster would make it an unparalleled laboratory for testing theories of black hole formation and growth. An object of 800 solar masses, if it were a single black hole, would have a physical size defined by its event horizon, the point of no return, of only about 4,700 kilometers in diameter, less than half the diameter of the Earth. Yet this tiny, invisible sphere would be the gravitational anchor for an entire stellar cluster, its influence felt across light-years of space. The hypothesis is simple and elegant. At the very heart of Messier 4, a place where mass segregation has been at work for over 12 billion years, the cluster's heaviest component, a single, dark, intermediate mass black hole, has settled into the gravitational throne room, and the rapid waltz of the surrounding stars is the celestial court paying it gravitational homage. This single object could elegantly explain the observed velocity dispersion, the excess speed of the core stars, without the need for more complex and contrived explanations. The hunt for the source of the hidden mass becomes a hunt for this specific object, this missing link, a search for the gravitational echo of a single, silent, mid-sized monster sleeping at the center of the ancient stellar city. The implications would be profound, suggesting that the dense cores of globular clusters are the natural nurseries for these elusive objects, the very places where the seeds of future supermassive black holes might be forged. If an intermediate mass black hole of 800 solar masses does indeed reside at the center of Messier 4, its existence begs a fundamental question: how did it form? A single star, no matter how massive, cannot directly collapse to form a black hole of this size. The physics of stellar evolution places a firm upper limit on the mass of stellar black holes at birth, likely no more than a few dozen solar masses. Therefore, an IMBH must be the product of more exotic, collective processes that could only occur in the most extreme and densely populated stellar environments, such as the core of a young globular cluster. One of the leading scenarios for IMBH formation is known as runaway stellar collision. In the very early days of Messier 4, billions of years ago, its core would have been even more compact and crowded than it is today. This primordial core would have been filled with a dense population of the most massive stars, each burning through its fuel with furious intensity. In such a dense environment, direct physical collisions between stars would have been not just possible, but frequent. When two massive stars collided, they would merge into a single, even more massive object. This new superstar would itself become a larger gravitational target, increasing its likelihood of further collisions. A chain reaction could ensue, a runaway process where a single, rapidly growing star consumes its neighbors in a series of violent mergers. This process would continue until the central star grew to hundreds or even thousands of solar masses. Such a hypermassive star would be incredibly unstable, burning through its immense fuel reserves in only a million years or so before its core imploded under its own colossal weight, collapsing directly into an intermediate mass black hole without a traditional supernova explosion, swallowing itself whole. A second plausible pathway involves the growth of a smaller, seed black hole. Imagine that one of the first, most massive stars in the young cluster collapses to form a standard stellar mass black hole of, say, 20 solar masses. Due to mass segregation, this black hole would quickly sink to the exact gravitational center of the cluster. From this privileged position, it would act as a cosmic predator. Its powerful gravity would capture and consume any unfortunate stars, gas clouds, or other compact remnants that strayed too close. Over billions of years, through a slow, steady diet of stellar material, this initial seed could gradually grow in mass, accreting its way up into the intermediate mass range. This process would be punctuated by more dramatic growth spurts if other stellar mass black holes, also sinking to the center, were captured and merged with the central one. The core of the globular cluster would become a gravitational funnel, channeling its heaviest components down into the waiting maw of the central, growing black hole. A third, more speculative possibility is that IMBHs are not formed within clusters but are primordial in origin. According to some cosmological models, density fluctuations in the ultra-hot, ultra-dense plasma of the very early universe, moments after the Big Bang, could have been so extreme that they collapsed directly into black holes of various sizes, including those in the intermediate mass range. These primordial black holes would then have acted as gravitational seeds around which the first structures, including globular clusters like Messier 4, later formed. In this scenario, the cluster would have formed around its IMBH, rather than creating it. Distinguishing between these formation channels is one of the great challenges of modern astrophysics. Each scenario paints a picture of a universe capable of forging these objects through violence and persistence. Whether through the spectacular, rapid pileup of colliding stars, the patient, eon-long consumption of its neighbors, or as a relic from the dawn of time itself, the potential presence of an IMBH in Messier 4 provides a tangible link to these fundamental and dramatic cosmic processes. The silent gravitational influence felt today is the lingering echo of a chaotic and formative past, a testament to the extreme physics that governs the hearts of these ancient stellar systems. The existence of an 800 solar mass black hole at the center of Messier 4 would leave more than just a subtle imprint on the velocities of surrounding stars, it would actively sculpt its immediate environment, creating a series of distinct, observable signatures. The most fundamental effect would be the creation of a gravitational sphere of influence, a region of space around the black hole where its gravity dominates over the collective pull of the rest of the cluster's stars. For an object of this mass within a cluster like M4, this sphere of influence would be relatively small, perhaps a fraction of a light-year in radius, but within this zone, the black hole is the undisputed gravitational king. Any star or object entering this region has its fate tied directly to the central mass. Over billions of years, the IMBH's gravity would systematically alter the stellar distribution around it. It would create what is known as a density cusp, a sharp increase in the number of stars per unit volume as one approaches the central black hole. Stars on orbits that bring them close to the IMBH would have their paths deflected, and through complex gravitational interactions, the stellar density profile would rearrange itself, with stars piling up around the central mass. The search for such a stellar cusp, a subtle but predicted increase in brightness and star counts at the very center, is a key observational test for the IMBH hypothesis. Furthermore, the IMBH would not be a completely quiet resident. While the space in a globular cluster core is largely empty of free-floating gas, preventing the formation of a large, bright accretion disk like those seen around supermassive black holes in active galaxies, occasional feeding events are expected. A star on a particularly unlucky, eccentric orbit could pass too close to the black hole, within its tidal radius. At this point, the gravitational gradient across the star becomes so extreme that the pull on the near side is significantly stronger than the pull on the far side. This tidal force would stretch and then violently shred the star apart, a process known as a tidal disruption event, TDE. The stellar material would be pulled into a temporary, brilliant accretion disk, spiraling into the black hole and releasing a powerful, multi-wavelength flare of radiation, in X-rays, ultraviolet, and visible light. Such a flare, though rare, perhaps occurring once every 10,000 to 100,000 years in a given cluster, would be an unambiguous, smoking gun, for the presence of a massive black hole. Detecting even one such event from a globular cluster would provide incontrovertible proof. The IMBH would also act as a powerful gravitational slingshot. The core of the cluster is a chaotic dance of three-body interactions, where a single star might encounter a binary star system, or two stars might pass close to the central black hole. In these complex gravitational encounters, energy and momentum are exchanged. The IMBH can dramatically amplify the outcomes of these interactions. It can capture one star from a passing binary pair, while violently ejecting its companion out of the cluster entirely. These ejected stars, known as hypervelocity stars, would be flung into the galactic halo at speeds of hundreds of kilometers per second, far exceeding the cluster's escape velocity. The discovery of stars originating from Messier 4 but now traveling at incredible speeds through the galaxy would be strong circumstantial evidence for the powerful gravitational engine at its core capable of producing such ejections. The gravitational footprint of an IMBH is therefore multifaceted. It is written in the static distribution of stars forming a central cusp, in the potential for rare but cataclysmic flares from devoured stars, and in the high-velocity exiles it kicks out into interstellar space. These are the secondary clues, the environmental impacts that astronomers search for to corroborate the primary evidence written in the simple, yet profound, acceleration of the core's orbiting suns. In the intricate quest to map the gravitational landscape of Messier 4's core, astronomers have a remarkable set of natural tools at their disposal: the cluster's population of millisecond pulsars. A pulsar is the rapidly spinning, highly magnetized remnant of a supernova, a neutron star. Its powerful magnetic field channels beams of radio waves out from its magnetic poles. As the star spins, these beams sweep through space like the beacon of a lighthouse. If one of these beams happens to sweep across the Earth, our radio telescopes detect a pulse of energy with astonishing regularity. Millisecond pulsars are the oldest and fastest of this class, spun up to rotational speeds of hundreds of times per second by accreting matter from a companion star in a binary system. Their rotational stability is so profound that they rival atomic clocks in their timekeeping precision. The arrival time of each pulse can be predicted with microsecond accuracy over periods of years and even decades. This makes them extraordinarily sensitive probes of their local environment. Any force that perturbs the pulsar's motion, even slightly, will cause a tiny but measurable delay or advance in the arrival time of its pulses. Messier 4 is unusually rich in these cosmic clocks. A significant number of millisecond pulsars have been discovered within its boundaries, many of them concentrated towards the core, exactly where they are most needed. This collection of pulsars forms a natural, pulsar timing array. By monitoring the pulse arrival times from each of these objects over many years, astronomers can create a detailed, three-dimensional map of their motions and, by extension, a map of the gravitational field they are moving through. If there is a massive object like an IMBH at the center of the cluster, its gravitational pull will affect the orbit of every pulsar. A pulsar orbiting the IMBH will experience a continuous acceleration, causing a systematic, predictable drift in its pulse timings. Even pulsars far from the center will feel the collective gravitational potential of the cluster, a potential that is dominated by the IMBH in the central regions. By meticulously analyzing the timing data from the entire ensemble of pulsars, scientists can build a model of the mass distribution within the cluster. They can test different models, one with just the visible stars, one with a diffuse dark component, and one with a single, point-like massive object at the center. The model that best reproduces the observed timing variations of all the pulsars is the one that most likely represents the true mass distribution. This technique is powerful because it is independent of observations of normal stars. It does not rely on measuring the Doppler shifts or proper motions of faint, crowded stars, which can be subject to systematic errors and uncertainties. Instead, it relies on the exquisitely precise and objective measurement of time. The chorus of compact objects, each pulsar singing its steady, rhythmic beat, provides a gravitational symphony. The conductor of this symphony is the total mass distribution of the cluster. A central IMBH would act as a powerful lead instrument, its gravitational solo subtly altering the tempo and rhythm of every other player in the orchestra. The analysis of pulsar timing data from Messier 4 is a long-term, patient project. It requires years of continuous observation to detect the minute, cumulative effects of the cluster's gravity on the pulsar's orbits. But the potential payoff is immense. This method offers one of the cleanest and most robust ways to either confirm the existence of the 800 solar mass IMBH or to rule it out in favor of alternative explanations. The pulsars, born from the death of ancient stars, now serve as the cluster's most articulate witnesses, their steady radio whispers carrying the precise gravitational truth of what lies hidden in the core. They are the ultimate insiders, reporting directly from the heart of the mystery, their testimony written in the fundamental fabric of spacetime itself. While the hypothesis of a single, intermediate mass black hole provides a compelling and elegant explanation for the observed stellar motions in Messier 4, it is not the only possibility. Science advances by rigorously testing competing ideas, and there exists a significant alternative model that could also account for the hidden mass. This alternative proposes that the excess gravity does not come from a single, monolithic object, but from a dense, centrally located cluster of stellar remnants. This would be a dark cluster within the larger globular cluster, a graveyard of the first generation of massive stars, concentrated at the very center by the same process of mass segregation that would cause an IMBH to sink there. This unseen subcluster would be composed primarily of dozens, or perhaps even over 100, stellar mass black holes, each with a mass between 10 and 20 times that of the Sun, along with a dense population of heavy white dwarfs and neutron stars. From a distance, the collective gravitational influence of this swarm of dark objects could be very difficult to distinguish from that of a single IMBH of the same total mass. If 40 black holes, each with 20 solar masses, were packed into the central light year of the cluster, their combined mass of 800 solar masses would accelerate the surrounding stars in a very similar way to a single 800 solar mass object. Both scenarios place the same amount of mass in the same general location. The key difference lies in how that mass is distributed. An IMBH is a true point mass, a singularity. The dark cluster, by contrast, is an extended distribution of mass, albeit a very compact one. This subtle difference in distribution should, in principle, create slightly different gravitational signatures. For instance, the shape of the stellar density cusp would be different. A single IMBH creates a steep, singular potential well, leading to a very sharp, strong cusp. A distributed cluster of remnants would create a broader, shallower potential well, resulting in a less pronounced, weaker cusp. Teasing apart these subtle differences requires incredibly precise measurements of star positions and velocities at the very limit of what current technology can achieve. Furthermore, the long-term dynamical evolution of these two scenarios is different. A central cluster of stellar mass black holes is not a stable configuration over billions of years. The black holes within this subcluster would constantly interact with each other gravitationally. These interactions would lead to frequent ejections, as three-body encounters tend to kick the least massive member out of the system. Over time, the subcluster would evaporate, losing members until only a tight binary or, eventually, a single, merged black hole remains. The question is one of timescale. Has Messier 4 had enough time for such a subcluster to dissolve, leaving a single IMBH behind? Or could a dynamically active subcluster still persist today? Some models suggest that such a system could indeed survive for the age of the universe, constantly evolving but still present as a collection of objects. The challenge for astronomers is to find an observable that can definitively break the degeneracy between these two models. This might involve looking for the faint, flickering X-ray signatures from the many individual black holes in the subcluster as they occasionally accrete small amounts of interstellar gas, which would present a different signal from the potential single source of a TDE from an IMBH. Or it could involve statistical analysis of the pulsar timing data, which might be sensitive enough to detect the lumpiness of the gravitational field from a collection of black holes versus the smooth field of a single one. The existence of this plausible alternative underscores the cautious, evidence-based nature of scientific inquiry. The case for an IMBH in Messier 4 is strong, but the verdict is not yet in. The silent, central darkness could be a solitary monarch, or it could be a tightly packed council of dark elders, both holding court over the luminous stars that surround them. The search for the true nature of the central mass in Messier 4 is more than a localized astronomical curiosity. It is a crucial piece of a much larger puzzle that spans the entire history of the cosmos, from the formation of the first stars to the evolution of the vast galaxies we see today. The question of whether intermediate mass black holes exist, and whether globular clusters are their primary nurseries, has profound implications for our understanding of the cosmic ecosystem. Supermassive black holes, like the 4 million solar mass Sagittarius A at the center of our own Milky Way, did not appear overnight. Their immense size suggests a long history of growth, but the origin of their initial seeds remains one of the great unsolved problems in cosmology. If IMBHs with masses of hundreds or thousands of suns can form efficiently in the cores of dense stellar systems like globular clusters, they provide a natural and compelling solution to this seeding problem. One prominent theory of galaxy formation, known as hierarchical assembly, posits that large galaxies like the Milky Way were built up over billions of years through the merger of smaller protogalactic fragments. In this picture, globular clusters are not just ancient relics but are the surviving cores of some of these primordial building blocks. If each of these building blocks contained a central IMBH, then as they merged to form the nascent Milky Way, their central black holes would have sunk to the center of the new, larger galaxy. There, they would have merged with each other, gradually building up the central supermassive black hole over cosmic time. In this scenario, the supermassive black hole at our galaxy's heart is the result of a long series of cannibalistic mergers, a composite entity built from the hearts of the very systems that formed the galaxy's halo. Finding a robust population of IMBHs in globular clusters today would provide powerful evidence for this model of coevolution, linking the smallest scales of stellar dynamics to the grandest scales of galaxy assembly. Messier 4, by virtue of its proximity, serves as our primary test case. Confirming an IMBH within it would be a watershed moment, suggesting that countless other globular clusters, both in our galaxy and in others, also host these missing links. This investigation thus returns us to the grandest scale, connecting the subtle dance of a few hundred stars in a nearby cluster to the fundamental architecture of the universe. The light from Messier 4, having traveled for 7,200 years, arrives not just as a pretty picture, but as a complex physical artifact, a time capsule carrying information about processes that govern the dawn of the cosmos. The patient work of measuring stellar velocities, timing pulsars, and modeling gravitational dynamics is a form of celestial archaeology, an attempt to reconstruct a history written in the invisible ink of gravity. The final answer to the mystery of Messier 4's core, whether it holds a single IMBH or a dense congregation of stellar corpses, will refine our narratives of creation. It will tell us whether the path to cosmic gigantism is a smooth and steady accumulation or a chaotic and violent series of mergers. It speaks to the limits of our perception, reminding us that the universe's most massive and influential components are often the ones that do not shine. The story is a testament to the scientific process itself, a slow, methodical accumulation of evidence, a careful weighing of competing hypotheses, and a deep respect for uncertainty. The profound silence at the heart of Messier 4 is not an absence of information, but a challenge to our ingenuity, a puzzle posed by the universe, waiting across the millennia for a species on a small, blue planet to build the instruments and develop the understanding required to finally read the answer written in the motions of its ancient, silent stars. The ongoing processes within this stellar city, the slow gravitational sorting and the intricate orbital dance, are a continuation of a story that began over 12 billion years ago, a story whose next chapter is still waiting to be deciphered.